Hello and welcome back for another video in the College Algebra playlist. In this particular video, we're going to start something that's really fun. We're going to just do an introduction to what matrices are. Matrices are used in all kinds of applications, from business to computer science to physics to biology to chemistry, all over the place. Matrices are a big part of solving what are known as linear equations. So matrices are huge, but they're also just a lot of fun. And they don't really require any high-powered mathematics. So mostly they involve add, subtract, multiply, and divide. So most students really like matrices and they think they're a lot of fun. Now, we're not going to spend a lot of time here. We're going to have two sections where we look at matrices. In this first section, we're going to introduce matrices, learn how to add, subtract, multiply by a constant, and then we'll learn how to multiply two matrices together. In the next video, we're going to learn how to solve some linear systems of equations using matrices, which is a very effective use of matrices, and they can solve very, very enormous and complex systems very, very quickly. So I'm glad you're here. Let's go ahead and get started. And I'm trying to find something on my window. There it is. Don't you hate it when you're looking on your computer and you know where it should be and you can't find it? It's so annoying. Okay, let's go ahead and take a look at matrices. And what are matrices? Matrices are basically arrays. The word array, A-R-R-A-Y. So it's an array. It's rows and columns of, well, whatever items you want to put into your matrix. Now we're going to be looking at numerical matrices. So we're going to have rows and columns of numbers. That's basically what it is. So it's like a complicated list in a table format. And that's what we're going to be looking at. Now, there are different ways to offset these tables of numbers so that you know it's a matrix. And the one that our textbook uses are the square brackets that you'll see right here on the left and on the right of this particular matrix called C. So when we're looking at this matrix, we can see those right there, right? I got to figure out why my cursor is not cursoring like it's supposed to be doing. All right, so when I'm looking at them, you can see that I've got these square brackets on either side. Now, some textbooks use round parentheses instead, just great, big, enormous round parentheses. And that's okay too. If you do that, then that's fine with me. You'll need to ask your instructor, make sure that it's okay, whatever method you're using. So again, sometimes we might see something like A might be written using the round parentheses. So you would see 1, 2, 3, and 4 in those round parentheses. I'll stick with the square ones for this video, but again, it's done both ways. Now, we do tend to name matrices with uppercase letters starting with A, so A, B, C, D, E, and so on. We don't have to, it's just our habit, all right? So when you look at this sort of table of numerical data, now, again, it doesn't have to be numerical, but we're going to study numerical ones. We have to have some kind of order so that you know which element I'm talking about. So each entry in this sort of table or array of numbers has a subscript. Now, a subscript is written below and to the right, and it's a pair of numbers that indicate what row it's in and what column it's in. And it's always given in that order. So it's row and then column. So I tell my students to think of Roman Catholic or RC Cola, RC. It's got to be row and then column. So when we're looking at this example right here, let's say that I want to look at this 2 that I've got right there. So when I'm looking at the 2 and I'm asking someone and I want to talk about the 2 and I want to think about what it is and where it is, I need to be able to tell someone what it is and where it is. So what I tell them is it's in row 2, column 2. So when I write it down, I would write A sub 2, 2 equals 2, indicating that in the second row, second column, I have the entry or the item or the element 2. Now I can do a different one if I want to. I could take a look at this -1 that I have up here, and then I would say, well, that's in row 1, column 1. I seem to be picking everything on the main diagonal, which gives me a -1. Now, if I wanted to, I could take a look at this 3 that I have right here, and then I would be able to write down that it's in row 3, column 1, and the entry is 3. Now, A31 is not the same as A13, so you have to be very, very careful. A13 would be row 1, column 3, and I don't have a column 3 in the matrix C, so you have to be careful. So when we're looking at these, we also talk about the size or dimensions of the matrix. Now, dimension for a matrix can also have a secondary meaning, so you need to be very clear if you go further in your study of matrices, which one you're talking about. Size is a little bit more precise. Actually, when we're talking about matrices, what size is it? What we're asking for is how many rows and how many columns. And that gives us an idea of the size of the matrix. It also tells us exactly how many entries it has, because we can multiply the number of rows by the number of columns, and that's how many entries we have. So when we look at these right here, and I look at, for example, matrix A right here, I would say that it has 1, 2 rows. So row 1 is 1, 2, row 2 is 3, 4. So it has 2 rows and it has 2 columns. The columns are given by 1, 3, that's column 1, and 2, 4 is column 2. So we say this is a 2 by 2 matrix. And the first 2 always represents rows, and the second one always represents columns. All right, so it's always RC. So RC Cola, it's your new favorite drink. Make sure you keep that straight. So let's take a look now at matrix B. If we look at matrix B, I have 3 rows. 1, 2, 7 is row 1. And then I have 0, -5, 6 as row 2, and 7, 8, 2 as row 3. I have 3 columns, 1, 0, 7, 2, -5, 8, and 7, 6, 2. And they're done in that order. So we go from the left to the right and from the top to the bottom. That's how we number. So the size of matrix B is a 3-row by 3-column matrix. So row, then column, 3 by 3. When we look at matrix C is not what we call a square matrix. Now, I'm not going to test my students on the definition of a square matrix, but square means, well, what is a square? It's a rectangle where the sides are all the same measure. So when you're looking at a matrix, a square matrix has the same number of rows as it has columns. So our matrix A and our matrix B are both square matrices, but C is not. So matrix is singular, matrices is plural. So you'll see up here at the top the word matrices, that's plural, and matrix, that's singular. So let's talk about the dimension of matrix C. So I've got two columns, but I've got 3 rows. -1, 3 is row 1, 0, 2 is row 2, 3, 1 is row 3. In that order, always left to right, top to bottom. And then I've got column 1, -1, 0, 3, column 2, 3, 2, 1. So the size of matrix C is going to be 1, 2, 3 rows by 2 columns. It's a 3 by 2. And because those numbers are different, it's not square, right? Now, square matrices have some unique properties, but unless you take a course in linear algebra, you'll probably never get to learn about some of the fascinating properties of square matrices. They really are truly amazing things. So again, we're going to take a look at these right here, and we're going to talk about these subscript numbers that you see on each one. That's the same as the subscript numbers that I was using up here. These down here are the same as what you're seeing right here. So for example, if we look at this matrix A now in the center of the screen, We've got a lowercase a sub 1, 1, a sub 1, 2, a sub 1, 3. The first subscript is a 1 because all three of those entries are in row 1. They're in different columns, so the second number changes. First column 1, then column 2, then column 3. And then in row 2, you'll see that all of the entries in row 2, the first subscript is a 2, indicating they're in row 2. And then their columns change, and you can see that coming across. If you look at the second subscript and you go down the columns, you'll notice those are all the same. Notice that this diagonal right here from upper left to lower right, we call this the main diagonal. And when you're looking at the main diagonal, notice that all of the entries on the main diagonal have the same subscript values. So this is our main diagonal. So let me highlight that for you down here. It becomes more important when we're talking about using matrices to solve more complex systems of linear equations, all right? So maybe a 5-variable, 5-equation system. Now, we talked in a previous video about solving systems of nonlinear equations, but we're going to be using matrices to solve some linear ones. But as you can imagine, doing substitution or addition elimination on a system with 5 variables and 5 equations is an enormous amount of work, and matrices shorten up that work and make it much more possible to do it without error. Not that error doesn't happen, but just so you know. All right, so this is what we call the main diagonal, right? Or the major diagonal. Right? So upper left to lower right. And you can always tell you're on the main diagonal because the subscripts for each of the entries have the same digits for each one. Now let's look at this one and this one over here. Now these are special cases. This first one here that you see, A11, A12, A13, this is called a row matrix. And a row matrix gets the name because it consists of a single row. All row matrices are single rows, so they're all row 1, basically, all right? But they might have many, many columns. And then, of course, what do you think we called the one over here on the right? Well, of course, we call this a column matrix because it only has one column, but it has multiple rows. So we can have a row matrix, which is one row, or a column matrix, which is one column, but multiple rows, or we can have a matrix with multiple rows and multiple columns. And you'll notice that all of these are using the square brackets around it. So let's get to the formal definition for what a matrix is, which is right here. It's a rectangular array of numbers. There's that word array right here, A-R-R-A-Y, which just means it's like a table, a grid of numbers that is usually named by a capital letter, usually beginning at the beginning of the alphabet, A, B, C, and so on. Each element, each entry in the matrix gets a lowercase letter name. So if I were going to call something B, for example, if I were going to use a matrix and name it B, and I were going to do, oh, I don't know, 4, 7, 8, 42, right? Then I would probably use lowercase b to refer to these entries. And if I were using uppercase C for the name, I would use a lowercase c for the entries. So for this one, I would say that B11, first row, first column, equals a 4. B12, now is that first row, second column, or second row, first column? RC. So this is going to be first row, second column, and that's going to be a 7. And then I've got second row, first column, which is an 8, and second row, second column, which is 42, right? So we tend to use the same letter for each entry, but a lowercase letter. These are sometimes referred to as A sub ij or B sub ij, and sub stands for subscript. So a subscript is written below and to the right, and that's where we put these numbers that you see right here. So let me Make this a little smaller so we can see it. These numbers right here, these are our subscript numbers, right? And when we refer to them, we call them sub ij. If I just want to be general and I don't want to talk about a specific one, I just say a sub ij or b sub ij. And that means one of the elements in the matrix named capital letter B, right? And the first one always represents the row. The second always represents the column. And we refer to their size or their dimensions by rows by columns, always RC. And this pattern of rows then columns continues throughout, for example, multiplication, where we take a row and multiply it by a column to get an entry. So this pattern is going to continue. Now let's take a look at a couple of problems here where we're just identifying different parts of a matrix. So in problem number 1, it asks us to find a sub 1, 4. So don't read it a sub 14. It's not a sub 14. Those are separate numbers. It's not one number. So that's a sub 1, 4, first row, fourth column. So we go to the first row, which is up here, and the fourth column, which would give me a 4, right? First row, fourth column. So one way that students think about doing that is they highlight the row and highlight the column, and they look for the number that got double highlighted. That is the entry in that position, first row, fourth column. Now let's take a look at A21. So if we're going to look at A21, then we should be looking at the second row, first column. So again, we're going to highlight the second row, and we're going to highlight the first column. And that's also a 4. Maybe I didn't pick a very good example to do. These should be different. Maybe it's good that you have to think about where it is. Where's a sub 3, 3? Now a sub 3, 3, because the digits are the same, it must be on the major diagonal, the main diagonal. And remember that main diagonal is coming from upper left to lower right in a line like this. Now this is not a square matrix, so it doesn't reach the bottom right. And that's typical when they're not square matrices. So when I'm looking at this one, what I'm trying to find is third row, third column. So third row, third column, and oh, well, what do you know? It's also a 4, right? So I hope this makes sense to you, how we specify which one we're talking about. The rules for multiplication of matrices are very specific. We have to multiply a very specific entry by another entry, and we're going to take a row and multiply by a column, each element one at a time. So we're moving across the row and down the column at the same time. Now let's look at problem number 8, which is just asking us for the dimensions. Again, it is rows, columns. So on this one, I have one row. This is a row matrix. And I have 3 columns. So I give the number of rows first, then I give an x, not variable x. This is a times, like a by, 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 and 3 columns. So this is a 1 by 3. Okay. Let's now talk about adding and subtracting matrices. Now, students actually love the adding and subtracting. They're like, oh my gosh, this is so easy. This is so awesome. What a great way to finish a college algebra class. It's okay. I don't know how else to say it. It's not as difficult as what we did, for example, in chapter 5. Chapter 5 was just so difficult with the rational equations and the rational functions and the factor theorem and the rational root theorem. Those concepts are really difficult. When we add and subtract matrices, it makes sense what we're doing and why we're doing it. So for example, one thing that you have to consider is that they have to be alike. So just like in math, if we have x squared plus x minus 3, and I want to add to that 3x squared plus 2x minus x cubed, I can only add together things that are alike. So I can add the 2x squareds, the 1 and the 3, to get 4 because they're both x squared terms. They're alike, right? So we have like terms. And I can add the x and the 2x to get 3x because they're alike. but the constant 3 and the x cubed term are not alike. So I can't combine those. All I can do is list them side by side. Now, when you're adding matrices, if they're not alike, you can't even add them. It doesn't make any sense. Usually, when you're solving a problem, the rows mean something. They have a physical, real world meaning, and the columns mean something else. So you might be tracking number of pounds of cashews, Brazil nuts, and peanuts. So you've got the number of pounds, and then you've got something else in the other column. So when you're looking at it, it means something. So you can't take that matrix and add it to one that maybe does cashews, Brazil nuts, peanuts, and another nut, almonds, right? Because the first one didn't have a column for almonds. So how can I add those bits of information together? It doesn't make sense. So this is a requirement. They have to have the same dimensions, like adding like terms. If they don't have the same size, we can't add them together. So if I want to add something to a 2 by 2 matrix, it has to be another 2 by 2 matrix. I can't add a 2 by 2 matrix to a 2 by 3 matrix because they're not alike. So in order to add or subtract, they have to have like dimensions, the same dimensions, same size. Now, if you got to pick the rule and you started with a 2 by 2, it makes sense, like what we did over here when we were adding together our x squareds and these sorts of things. It makes sense that when we add 1x squared and 3x squared, we still have x squareds. So it would make sense if I'm adding a 2 by 2 to a 2 by 2 that I still have a 2 by 2. And in fact, that's the rule. So it makes sense that we're still looking for something with the same dimensions that each of the summands had. Now, what would be the obvious rule? Well, I guess you could come up with complicated rules, but the simplest rule you could come up with is take the A11 and the B11 and add them together. So 4 plus 3 would give me 7. That's the simplest rule. Well, then how would you get, say, the one in the 1, 2 position, first row, second column? Take the ones in the first row, second column position and add them together. So 5 plus 0 gives me 5, all right? So we're just doing this one at a time. So again, I would take the number in the 2, 1 position, second row, first column, and add them together. -1 plus a -4 would give me a -5. And then the last one, I'm just about out of highlighting colors, would give me 2 plus 8, which gives me 10. So it's a new 2 by 2 matrix, but it has the same dimensions as the 2 I was adding together. And the rule is add the corresponding entries in the same position together, and that gives you your result. Not too bad, is it? Right? It's addition, right? Arithmetic. How about subtraction? Well, subtraction turns out to be the same rule, just instead of adding, you subtract, and it's going to go in the order that it's written. So for example, if we were to change this problem, so if you want to pause the video and finish copying it down, do that now. Okay, good. And after that, let's change this problem now. So let me wipe out my solutions here. And let's say that instead of adding, I wanted to subtract instead. Well, then the rule would be take the 1 in the 1, 1 position, the 4, minus 3, which would give me a 1 in the 1, 1 position. And then take the element in the 1, 2 position, 5, subtract 0. That one actually didn't change, right? And then take the 1 in the 2, 1 position, second row, first column, -1, minus a -4. Be careful with those double negatives. It's easy to make careless mistakes in matrices. I don't see as many conceptual errors in matrices, but I do see a lot of careless mistakes. You want to be careful, make sure that you write everything out, use lots of space. Don't crowd up your work. That's when you tend to make more errors. And try not to do it at 3 o'clock in the morning, because you're tired and you're more likely to make small mistakes like that. So we have -1 minus a -4, which makes it +4. So this is going to give me a 3. And 2 minus 8 gives me a -6. So this is the rule for addition and subtraction. Now, because addition and subtraction of numbers, or because addition of numbers is commutative, it turns out that A plus B would give me the same as B plus A. This is not the case for multiplication. Matrices are a little bit different in that multiplying A by B probably will not give you the same result as B times A. In fact, you might not even be able to do B times A. You might be able to do one and not the other, right? So in general, we have to sort of go back through all the rules that we know and make sure they really work for matrices. So commutativity of addition does still hold. Obviously, subtraction, you can't switch the order, but if you do switch the order, what does it do to the matrix? Well, it just makes every element negative, the opposite sign. So it's like multiplying by a -1. Now they're also associative, which means if I have 3 matrices to add together, I can add 2 of them first and then add the third in whichever order I want. Because with the commutativity, I can reorder them so that I can do any pair first and then the last one. Or you can add them all together all at once. So let's take a look at problem number 2, which we have a 2 by 2 matrix here plus a 2 by 2 matrix here. And I recommend when you're learning about matrices that you go ahead and write down the dimensions from the very beginning, because you cannot add or subtract if they're not the same. And the rule for products is different, but without writing down the dimensions, it's very difficult to tell whether or not you can multiply them together. So make sure you go ahead and write them down. So I have a 2 by 2 times a 2 by 2, which will give me another 2 by 2. These are added together. So -1 minus 3. So I'm looking at the -1 plus a -3. So, and some students even like to do it like this. So I'm going to show you a way of trying to prevent careless mistakes. They'll go ahead and write down -1 plus -3. Right? So they're just going to write that. And then for the next one, they're going to come over here and they're going to say 1 plus 5. And so they'll write 1 plus 5, right? And then they'll come over here and they'll do another 1 plus 5, because we had the same numbers in the same locations. And then we have 8 plus a -3. So they write them down first, and then they actually go through and do the arithmetic last. So then it's very easy for them to check. So how do you check this? So looking at this one, I've got column 1, -1, 1. So I just check -1, 1. Yep, that's what I had. And then I added it to this column 1, -3, 5, -3, 5. Yep, I copied it right. And then I had 1, 8. Yeah, I've got 1, 8. And then I had 5, -3. Yep, 5, -3. So you do need to sometimes check that you've copied it correctly, because that's actually the biggest mistake that I see most of the time. So I get -4 for the element in A11, and I get 6 in the element for A21, 6 in the element for A12, and 5 in the element for A22. And notice that you don't even have to do them in order. You can do them in whichever order. It's not going to change what value goes in that entry. Let's take a look at another example. This one is problem number 3. This is a subtraction problem. So again, I'm going to use that method that we used last time, and I'm going to say that this is going to be 7 minus 6. And then I'm going to have in this 2, 1 position, I'm going to have -8 minus a -2. And then I'm going to have over here 2 minus 0 in the 1, 2 position. And then from the 2, 2 positions, I have 7 minus a -1. And then I can come through and I can check very quickly. 7, -8, check. 2, 7, check. 6, -2, check. 0, -1, check, and minuses in between. And then I know I've got it set up correctly, and I only have to worry about messing with the arithmetic. So this will give me a 1 in the A11 position, a 2 in the A12 position, a -6 in the A21 position, and an 8 in the A22 position. Let's try one that's a little bit larger. So for this one, when we look at this, again, I recommend go ahead and write down the dimensions. These become very important when we're doing products, but they're also very helpful for addition and subtraction. So I have 3 rows and 2 columns on the first one. So a 3 by 2 plus another 3 by 2. Do they have the same dimensions? Yes. So what's my result going to be? A 3 by 2, which in this system, it pretty much gives the game away because it's opened up that many holes for you. All right, so now let's go ahead and practice what we did the last time. So go ahead and pause the video, write them out, and then turn the video back on and let's compare and see if we got the same thing. Okay, don't compare yet because I've deliberately made an error. When I wrote these down, notice that I crowded my work up a little bit. And because I crowded my work up, I missed this negative on the 7. I read this as part of the plus sign. And I thought this was -2 plus a +7. But if I had checked and come over here and come down this column, it should be 2, 6, -7. And then I probably would have caught it. And that would make this number, of course, different. So let me fix my error now. I can take my note off. Better erase that first. And this should be a -9. Now, be very careful about crowding your work up when you're working with matrices. I cannot tell you enough times how important it is to use more space. Don't use lined notebook paper, use blank computer paper, and use a lot of space. The closer your numbers are together, the more likely you are to accidentally miss a negative like I just did, all right? Be very careful. Word to the wise. All right, so now let's go ahead and look at this next problem. Pause the video and work it out, and then turn the video back on. Now careful, this one's subtraction. Okay, so compare your answer to mine and let's see how you did. All right, notice that this one is a 3 by 2 and this one is a 3 by 2. So when I subtract them, I get a 3 by 2. I was more careful this time to leave more space between my numbers, especially if I have a sign in the middle followed by a negative. Leave space so you can see it. It helps if you actually write the negative a little higher than the normal symbol in the middle, and that way you're less likely to lose it. So when we were done, we again ended up with a 3 by 2. Now it's time to look at what is, with matrices, probably one of the more difficult things to do, which is, oh, wait, not yet. Hold off on that thought. The more difficult thing to do is multiply matrices. But first, we have to multiply by a scalar. That's not hard. So a scalar is just another word for a constant. So when we talk about a scalar, we're talking about a number, right? A constant number. For example, 5. Right? 5 is a scalar. -2, even pi, e. These are all constant numbers. They never change. They're the same value all the time. That's a scalar. So what we want to learn first, before we get to the harder multiplication of matrices, is how do we multiply a matrix by a scalar? So what I'm talking about is, suppose that I start with some matrix A, and this one was a 2 by 2, so let's just do another 2 by 2. And let's suppose I want to multiply A by the number 2, 2 being a scalar. So I want to come up with 2A. Well, the simplest rule would just be well, multiply all of A by 2. Well, let's just multiply each entry by 2. And that would be the simplest rule. And that, in fact, is the rule. So this becomes 2, 0, -8, and 6. So we took each original element of the matrix and multiplied it by that scalar. And that gives us that value. Now, because of the rules for arithmetic, we can find that the distributive property by a scalar also applies to matrices. So because we have the distributive property with numbers, we end up with a distributive property for matrices. So if I want to take a number like 2 and I want to multiply it times the sum of matrices A and B, I would get the same result if I took matrix A multiplied by 2, matrix B multiplied by 2, and then added those together. I'll get the same thing. So you can do it in whichever order you think makes the most sense, what is easiest for you, or what seems best for that situation. And it also turns out that if we have two scalars that we want to multiply by a matrix, then we can distribute the scalars as well. So we wouldn't do this very often if we had something like this, but if we didn't know what the scalars were, if one of them was a variable, then we might do something like this. Otherwise, it doesn't really make a lot of sense, because most students are going to look at this and they're going to say, well, if you've got 5 plus 3, that's 8. Yeah, so why wouldn't you do that? Well, it might be that you didn't know what one of them was. So you have a placeholder for one and a constant for the other. And then it turns out that this is the same thing as 5 times A plus 3 times A, which of course is going to give us, in this case, 8 times A. All right, so this is called scalar multiplication. So let's look at this problem right here. We have two matrices. We have A and B. So let's write down their dimensions. A has 3 rows and it has 3 columns. So it's a 3 by 3 square matrix. And when we look at B, if we want to add or subtract, they have to both be 3 by 3s. Now, if I want to multiply by a scalar, it can be any size I want, doesn't matter. So B is also a 3 by 3. So they do have the same dimensions. So I can add and subtract these if I like. So the first one says -2 times A. So what I'm going to do is I'm actually going to take the -2 and I'm going to multiply every single entry in the matrix A by -2, and I'm going to keep it in the same position. Doesn't change positions, it just stays where it is. So I'm going to write it out the longhand way, but honestly, I would do it in my head. And if I do it in my head, I figure most of my students are going to do it in their heads. The only thing you want to be careful of is on an exam, I can't grade what's in your head. So on an exam, you might want to take the time to write it out the long way like I'm doing here, so that your professor has more to grade in case you've made a simple mistake somewhere. And so they know what you're thinking. Otherwise, they might look at your numbers and go, how on earth did they come up with that? Well, you just multiplied wrong. So I'm going to write -2, 7, -2 times 5, -2 times -2, -2 times -2. I'm now going down column 2. -2 times -9, -2 times 1, and then -2 times, I am doing A, aren't I? Yes, good. -2 times 1, -2 times 6, -2 times -1. Now, if you write this down, this sort of protects you on your exam, because your professor can look at this and go, oh, they have the concept. They know what to do. And then if you make a ton of mistakes in the multiplication, they'll go, whoa, boy, they really need to work on their multiplication facts. But that's not what they're testing. So you're more likely to get partial credit. So we're going to end up with a 3 by 3 again. So this is going to be -14, -10. I don't know why I'm going down rows. I could go across columns as well. So let's just go across. So this is going to give me a 4, and this will give me a -2. And I'm probably messing you up because I'm going all over the place. But again, I want you to get the idea that which order you do these in is not affecting the result. All right. Notice that I'm leaving a lot of space between my columns. Don't crowd these together, because if you do, this might start looking like 101 and 8 instead of 10, negative 10 and 18. So you want to be careful and allow definite space between your columns. You also want to allow some space between rows. Neuroscience tells us that the brain processes the numbers much faster and more accurately if there's more white space on the page. And this is why I emphasize using blank computer paper. So for this next part down here, we have a minus 3b. And when we're looking at something like this, it says, okay, I want to take the element in A and I want to subtract from it 3 times the element in B. So you can do this a couple different ways. You could go off to the side and compute 3b and then take A minus 3b, or you can kind of put it all together. Now, this is another good way of writing it out longhand. So what I'm going to do is I'm going to take the elements from A, and I'm going to go ahead and write them down so I can keep track. And another good way to do it is take your finger and go down the column or across the row, make sure you're getting them right. And then I've got negative 2, negative 9, 1, 1, 6, negative 1. Now I'm going to check that. I wrote them down by column. I'm going to check by going across the rows. So I'm going to look at the rows here. 7, negative 2, 1, 7, negative 2, 1, 5, negative 9, 6, 5, negative 9, 6, negative 2, 1, negative 1, negative 2, 1, negative 1. It's very fast to check, and it will save you so much grief. So please take some time to check. Then what I want to do is subtract something. So I want to subtract 3 times something. So I'm going to put minus 3, minus 3, minus 3, minus 3, minus 3, minus 3, minus 3. Oops. See how close those got together? I need to fix that. Minus 3, minus 3. And then I want to multiply by something. So I need to put my number in parentheses, right? And again, this protects you on an exam because the professor can look at this and know at a glance that you have the concept. Maybe you're just messing up on the arithmetic. So I look at this, I was taking matrix A and subtracting 3 times matrix B. So matrix B, the elements are 7, 1, 7 down column 1, 8, 6, 1 down column 2, 5, negative 7, 5 down column 3. And then I'm going to check by going across rows. Row 1 would be 7, 8, 5. So I check in the parentheses 7, 8, 5, 1, 6, negative 7, 1, 6, negative 7, 7, 1, 5, 7, 1, 5. Okay, make sure you have the numbers written down correctly first. Then go ahead and do the arithmetic. So this will take me a little bit longer to do. So I'm going to pause the video, work it out, and then I'll turn it back on. Okay, so I've got them written down. And I will tell you, it makes me nervous to do this freehand because I'm always afraid I'm going to make a careless arithmetic mistake and then I'm really going to confuse my students. So hopefully that doesn't happen. If it does, let me know in the comments that I've got an error and I'll come in and fix it. So notice again that I wrote this one a little larger. Why? Most of my numbers were 2 digits and I had a lot of negatives. In order to allow more space between the columns, I had to stretch it out a little bit more. So don't be afraid to use more space. Just because they're both 3 by 3s doesn't mean they have to take up the same amount of space. Now let's take a look at this last one. I have negative 5 times A minus 5 times B, all right? Now, there are different ways of doing this one, all right? So one thing notice is we could factor out that negative 5. We could actually instead compute negative 5 times A plus B. Now, why would that be simpler? Well, then I would only be multiplying one matrix by the negative 5 instead of 2 matrices by negative 5 and then putting them together. So in some ways, it would be simpler to do negative 5 times A plus B, remembering that we do have the distributive property of a scalar over 2 matrices in matrix arithmetic. So this is the process that I'm going to follow. So what I'm going to do is I'm going to write this one right here. I'm going to put -5 on the outside of the matrix, which means I haven't multiplied it by -5 yet. And then I'm going to take and I'm going to add the elements of A and B together. So 7 plus 7 is going to give me 14. -2 plus 8 is 6. 1 plus 5 is 6. 5 plus 1 is 6. -9 plus 6 is -3. 6 minus 7 is -1. -2 times 7 is -14. 1 times 1 is 1. -1 times 5 is -5. Now, this time I didn't write it out. The danger is if I've made a mistake, sometimes the professor's looking at your work going, how did they get that number? Because it was just an error, all right? So again, on an exam, my recommendation is that you follow the process of writing it out longhand and then doing the arithmetic. Two things, less likely to make a mistake, more likely to get partial credit. And then I'm going to take this matrix and I'm going to multiply every element by the -5. So this is going to give me -5 times 14 is -70. Check me, make sure I get this right. -5 times 6 is a -30, and I better write smaller because I'm running out of room. -5 times 6 is a -30, and I'm really running out of room. And then -5 times 6 is another -30. -5 times -3 is 15. -5 times -1 is 5. What happened to my 5? It froze on me. Wake up, word. I have a 5. -5 times -14 would be a +70, double negative. -5 times 1 is -5, and -5 times -5 is 25, right? Now, would I have gotten the same thing if I had multiplied A by -5 and multiplied B by 5 and then subtracted it from -5 times A? Yes. The only thing you want to be sure you don't do is multiply B by a -5 and subtract. There's only one negative in there. So you either need to think of this as -5A plus a -5B, or -5A minus a +5B. So whichever way, make sure you're only using one negative there. Now we're ready for the hard stuff. All right, so it is complicated. I'm not going to lie to you. It is way more complicated than adding, subtracting, and multiplying by a scalar. It is more difficult, and the logic is harder to see. But I will tell you that it does make sense when we work it out with real world meanings. All right, so it does make sense in that aspect. Unfortunately, in a college algebra class, we don't do as many real world applications, although we'll do some, right? So you could take number of pounds of cashews, number of pounds of Brazil nuts, number of pounds of peanuts, and then you can multiply that by the price per pound, and that will give you the cost of that many pounds. So you set it up in a matrix like that, and you can figure out the total cost, right? So when we're looking at multiplying matrices together, it's a weird rule, which is they don't need the same dimension. The inner dimensions have to match. And this is why I've been emphasizing that you need to write them down. So what I mean is that this pair right here, this pair has to match the one that's there on the inside. So, and I have to write them down in order, right? Because just because I can multiply A by B on the right doesn't mean I can multiply A by B on the left. I know, what? And we're so used to multiplication being commutative, 3 times 5 equals 5 times 3, that the idea that that doesn't always work is a little mind-blowing, but it's because of the way that we define the product process. So for example, let me write out what it would look like if we tried to do it in reverse order. So this is B times A, and B is a 3 by 3, and we're multiplying it by a 2 by 3. Notice that this inner pair do not match. And that's a problem because we're going to be taking and we're going to be multiplying a row by a column. And if they don't have the same number of elements, we can't do it. And that's a problem. So when those inner dimensions don't match, the row and the column we're trying to multiply together don't have the same number of elements. They don't match up. So we have to be sure they have the same, but it's a row from one and the column from the other. And that's why we're using those inner dimensions that have to match. So notice that this one is not even defined, does not exist, all right? We can't do B times A, but we can do A times B. So when we're looking at it over here, what we're actually going to do, I'm going to foreshadow, we're not quite there yet, but I want to foreshadow a little bit. We're going to be taking this row and we're going to multiply by this column, all right? So when we take this row and multiply by this column, notice that this row has 3 elements in it, and this column has 3 elements in it. And what are we doing over here? So we have 3 here. This is the number of columns. It's in row 1, but there are 3 entries because there are 3 columns. That's the 3 that we see coming from here. And then when we get to matrix B, it's in column 1, but there are 3 elements in column 1 because there are 3 rows. So the number of columns of the matrix on the left has to match the number of rows of the matrix on the right. And then when we multiply them together, we've got a 1-for-1 relationship. Because what I'm going to do next is I'm going to multiply A11 by B11. And then I'm going to multiply A12 by B21. And I need another color. I'm sure there's got to be another color. Yes. Okay. And then I'm going to multiply A13 by B31 and add all 3 of those together to go in the product. I know, right? It's a lot more work than adding and subtracting and multiplying by a scalar. But it does now make sense, I hope, why we have to have those inner dimensions match. The number of columns of the one on the left has to match the number of rows of the one on the right, so that when I pair them up, these 2 guys get multiplied together, and these 2 guys get multiplied together, and these 2 guys get multiplied together. And then I add those 3 numbers together, and that number actually ends up in that row and that column. So if it came from row 1 and column 1, then it goes right here, right? So how do we know the dimensions of the product? Well, it turns out the dimensions of the product come from the outer pair. So the outer side of the product of the 2 dimensions gives us the size of the product. So for example, the inner pair have to match, but when you're talking about the product's dimensions, it's going to be a 2 by 3, all right? So the inner pair have to match and they sort of disappear, and we get the outer dimensions as the dimensions of the product, all right? So this will be a 2 by 3. So there will be 2 rows and 3 columns. All right, let's now look at problem number 9, which is just asking us to figure out what the dimension of the product is. So it's not asking us to do the multiplication because they didn't even give us the matrices. Just if we did it, what would the size of the product be if it exists? If it doesn't exist, then we might enter D in E for does not exist. So if we're looking at B times A, that means B is on the left and B is a 5 by 2, and A is on the right, which is a 2 by 9. So again, we've got to make sure that the inner pair match. If the inner pair match, and they do, then the dimensions of the product are going to be this outer set right here. So it's going to be a 5 by 9, right? Let's take a look at part B, which is C times B. So C is on the left and C is a 9 by 5. And I sometimes will put them in parentheses like that so that I understand I'm multiplying them together. And then B was a 5 by 2. And again, I need to first check that the inner pair are exactly the same. when I multiply them, I need to make sure I've got exactly the same number of elements in the row multiplying by the column, and then it will match. All right, and then what I get is the outer pair. So this is going to give me a 9 by 2. And in that order, there will be 9 rows and 2 columns. So this one is going to be a 9 by 2. And now we want to do A times C. So A is a 2 by 9. And C is a 9 by 5. So again, make sure the inner pair match. They do, which means I'm going to get the outer pair in that order. I get a 2 by 5, right? So this will be my answer for that part right there. Let's take a look at this one right here. On this one, there's a possibility that they don't exist. If they don't exist, we'll write undefined. All right, so A times C. So if I do A times C, A is on the left, and the size of A is a 5 by 5. So let me write those separately. A is a 5 by 5. B is a 5 by 7. And C is a 7 by 8, right? So A times C, A on the left would give me a 5 by 5 multiplied by a 7 by 8. This time when I check the inner pair, those don't match. I can't multiply them together. I'm not going to have the right number of elements. I'm going to have 5 from the one on the left and 7 from the one on the right. What am I going to do? My rule won't work. And so in this case, we say that the product AC is undefined or does not exist. What about A squared? Now, A squared, you might be like, oh, I don't know how you square a matrix. I know how you square 5, but I don't know how you square a matrix. Well, just think of A squared as A times A. Now, this is a wild thing. You can't always square a matrix. You can't even always multiply it by itself. So A times A, you can really only square if it's square. Yeah, okay. Yeah, I know that's kind of a phrase that we use. You can only square if it's square. But A is a square matrix. It's a 5 by 5. And the reason you can only square if it squares, because that's the only way you're going to get the rows and columns to be the same, is if the rows and columns are the same. So you're going to have a square matrix. And then you will actually end up with one that is of the same dimension. So you will end up with a 5 by 5. And don't forget to use an X for the 5 by 5. And then we want to look at C times B. So C is a 7 by 8 and B is a 5 by 7. Now, when we look at the inner pair, these don't match. I can't do it. The one on the left is going to have 8 entries prepared to be multiplied one at a time by the 5 entries on the right. And that means I've got 3 extra on the left and I got nothing to multiply them by on the right. So I can't do it. It's not defined. All right. So that's not defined. Does that mean BC won't be defined? I don't know. Just because CB is not defined doesn't mean BC is also not defined. So I've got to check it individually. So BC reverses the order, and I get 5 by 7 on the left and 7 by 8 on the right. And now in this order, the inner pair do match, which is going to give me a 5 by 8 as the product. And so I can do the multiplication. It is going to work, and it's going to give me a matrix with 5 rows and 8 columns. Okay. We've got one more set to take a look at before we actually start with the multiplication. So let's take a look at this one. So we've got A, B, and C as our matrices. So A is a 7 by 3. B is a 7 by 3. And C is a 5 by 7. So the question is, can I do C times B, then subtract A? So C times B, the inner pair have to match. Then I'll get the dimensions of the outer pair. Then the dimensions of that have to match the dimensions of A to subtract it. So when I look at this, if I do C times B, I'm going to have a 5 by 7 multiplied by a 7 by 3. The inner pairs do match. They're both 7, so I get the outer pair. This gives me a 5 by 3. And I then subtract A. A is a 7 by 3. Can I subtract a 7 by 3 from a 5 by 3? No, they're not alike. So I can't. It's not defined. So which of these are defined? This one is a no. It is not defined. It is undefined. Not because the multiplication wouldn't work, but because the product gave me a 5 by 3 matrix and A is a 7 by 3. When you add and subtract, the dimensions have to match. When you multiply, the inner pair have to match and you get the outer pair. What about A times B? So let's move over here. So I have A times B. Well, that will give me a 7 by 3 multiplied by a 7 by 3. Well, the inner pairs do not match, so I cannot do that multiplication. So this one also does not exist. It is undefined. And let's now look at C times A. So this is going to give me 5 by 7 times a 7 by 3. The inner pairs do match, so I can do the multiplication, and I'll end up with a 5 by 3. All right. Let's take a look at the last two. The last two don't involve any multiplication, just addition and subtraction. Remember, I can only add or subtract if the dimensions are the same. So can I do B plus A? Well, yes, they're both 7 by 3s. So their sum would be a 7 by 3. So this one is a yes. What about C minus B? Well, no, C is a 5 by 7 and B is a 7 by 3. Those aren't alike, so no, I can't do it. So out of all of those options, only one was possible. Now it's time to talk about how to actually do multiplication of two matrices. I've kind of given you hints, but it's time to get our hands dirty and actually do it. Okay, so let's start with a not too easy problem, but not too complicated problem. We're going to start with matrices A and B and multiply them together. So this is matrix A here, and it's being multiplied by matrix B here, and we're ending up with matrix capital C here. You'll notice that A is a 3 by 3 and B is a 3 by 3. So when we look at these, the inner pair does match here. We have a 3 by 3 matching in the middle, which means that we get a dimension of 3 by 3, the outer pair here for the result. So when I look at this, where is C11 coming from? What numbers go in to make up C11? So what happens, and this is somewhat complicated, so make sure you're paying attention and really focused on what we're doing. We're going to start by taking row 1 and we're going to multiply by column 1. All right, so row 1, column 1. So if I'm using row 1, column 1, that's a 1, 1, and it's got to be row column. So 1, 1. That's going to go in the 1, 1 position in matrix C. So I'm going to multiply these together one at a time. Now I have to move across the row from left to right and down the column from top to bottom. So I'm actually going to be multiplying together, and I'm going to write it out in larger notation here so that you can see it. I'm going to have A11 times B11 plus A12 times B21 plus A13 times B31. Notice that when you do that, in each individual little multiplication, the inner pairs match, and it gives you the position of the final entry in the product. So for example, what I'm pointing out is that these are both 1 on the inside, and on the outside I have a 1, 1. These are both 2 on the inside, but again, I get 1, 1. And these are both 3 on the inside, but again, I get 1, 1. So I add all 3 of those numbers together. That one number becomes C11, right? All of that work to produce one number in the product. And then how would I get another position? So let's change our positions. Now, how would I get something in row 1, column 2? So for example, how would I get this one right here? Well, I'd have to take row 1 from the matrix on the left and column 2 from the matrix on the right and multiply those elements together. So let's go ahead and write those out here next to it. So this time, and I'm going to erase my, if I can, without erasing all my numbers. This time, we again are picking up row 1 from the matrix on the left, but this time we're picking up column 2 from the matrix on the right. All right, so now I'm going to multiply those together one at a time. This is why those inner pair had to have the same dimension, so I have the same number. So I'm going to have A11 times B12 plus A12 times B22 plus A13 times B32. And again, notice the inner pairs are all going to be the same on each individual product, and they all give you 1, 2 on the outside. They all come together to become part of C12. So this is how you can fill out the whole matrix all the way across. And I don't have enough space here for my third column, so you can see it can take quite a bit of space. And I recommend that you go ahead and use the whole page. You will, in this case, you'll have numbers you'll be multiplying together. And a lot of times what students will do is they will multiply the numbers together in their head, but they'll write down the individual products and then they'll do the addition in another step. So again, what we're doing here is we're taking row 1 times column 1, but we're taking each individual element and multiplying them together one at a time. And all 3 of those added together go in the 1, 1 position. So if I use row 1 from the left and column 1 from the right, it goes in the 1, 1 position. Where would it go if I used row 3 on the left and column 1 on the right? Row 3 on the left, column 1 on the right, it would be in the 3rd row, 1st position in the product. So we follow this process for all of the positions, and that's our product. That's our rule. So let's go ahead and talk about some of the properties of matrix multiplication. It's not like multiplication in arithmetic. It's not commutative in general because, again, the dimensions have to match. Just because A times B is defined doesn't mean B times A is defined unless they're square matrices. And so now what we're looking at of the same dimension is what's called the associative property. So assuming it's defined, if you have 3 matrices multiplied together and the dimensions work to actually do the products, you could do A times B first and then right multiply by C, or you could do B times C first and left multiply by A. Notice that the order in which they're written is the order in which they have to be multiplied, all right? So when we multiply B, C together, B has to be on the left and C has to be on the right. Here, B will end up, in a sense, being on the left and C is on the right. So that has to be maintained. We do have the distributive property in matrix multiplication, which is actually kind of surprising sometimes when you think about it, because it's not commutative, but we do have the distributive property. So C times A plus B does give me C times A plus C times B, and A plus B times C does give me A times C plus B times C. And you may look at this and go, well, I didn't know you had to do it differently from the left than you do from the right. You do with matrix multiplication, because multiplication from the left and multiplication from the right, they may not both exist. Okay? Again, it is not commutative. In general, A times B does not give you B times A. One may not even be defined. Let's go ahead and practice on this particular matrix here. So we have matrix B and matrix F. So matrix B is a 2-row by 3-column matrix. This is B. And F is a 3-row by 3-column matrix. Now the inner pair does match, and so we're going to get the outer pair as the dimension of the product. So it's going to be a 2 by 3. And you'll notice down here in the answer part that they did go ahead and give you 2 rows and 3 columns. Now what I want to do is I want to highlight each part as we go through and write it down. So I've copied them over and over and over again so I can do that. Obviously, you wouldn't do this if you were doing it on your own, but I'm doing it this way for teaching purposes. So because I know the result is going to be an 2 by 3, then I know that I can set up my locations. So I'm going to have a 2-row, 3-column matrix for the result. So I'm kind of setting up blanks here. Now, what's going to go in this first A11 position or C11, whatever you have right here? That is in row 1, column 1. So it must be coming from row 1 from the one on the left and column 1 from the one on the right. So now we're going to multiply the elements together one at a time, right? So what I'm going to have is 0 times 0, and I'm going to try to write really small. So these blanks are probably too large. All right, so let me get smaller blanks. I think I'm making them just as big, aren't I? Oh, very hard for me not to make them large. Okay, my last ones are really small. So in the first one, I've got 0 times 0 plus 2 times 1 plus -3 times 1. And notice my negative there got kind of buried in that plus. So I might want to circle it or something so that I know that it's there. So what number is going to go in that position? Well, 0 plus 2 is 2. 2 minus 3 is a -1. So I'm going to end up with a -1 in this position. So when I'm done, this number is going to be -1, right? So I'm still going to have something over here and something here, something here, something here, something here. But this one came from multiplying each of those together one at a time. Let's now look at another position. So let's just pick one at random. We don't always have to do it in the right order. We can look at a random one. So let's say that we want to take that row and that column. Where's it going to go? Where does it belong in the product? Well, I used row 2 and I used column 3. So if I used row 2 and column 3, it should go in row 2, column 3. So that's going to be this one right over here. So it's going to end up over here. So now I'm going to multiply them together. So let me make this blank a little bit longer. I'll shorten you up and extend you a little bit. So I'm going to have 1 times -1 plus 2 times 1 plus 0 times -2. And it always plus in between. You're always adding those products together. Now the product itself may be negative, but you're always adding them together. So this is a -1 plus 2, which is 1 plus 0, which is still going to be 0. So now I know that I have these two. I've got a -1 here, something here, something here, something here, something here. And oh, I forgot what it was. I've got a 1 and a 1 here, right? So I'm a third of the way there. All right, let's take another position and see what we get. So let's say that we want to take this row and this column, all right? So I'm taking row 1, column 2. So it's going to come over here in row 1, column 2. That's where it's going to fit when I get it done. So now I'm going to go ahead and multiply the elements one at a time. Now what I typically do is I actually use my fingers and I go across the row and down the column, putting the numbers together. And usually the numbers are fairly reasonable in exercises so that you can actually do them in your head and write down the product. But again, on an exam, I would write it out the long way so that you don't make a mistake that your professor can't figure out. So I've got 0 times negative 2. So I've got 0 times negative 2 plus 2 times negative 1 plus negative 3 times negative 3. All right, so when I multiply all that out, I've got a negative 1 here. I don't know what goes here. I'm figuring out that one. I don't know what goes here, and that's a 1. So here I'm going to get 0 minus 2 plus 9. Minus 2 plus 9 must be 7. So I get a 7 there, right? So hopefully this is making sense to you. I'm going to pause the video, or rather I'm going to ask you to pause the video, work out the 3 remaining ones, and then turn the video back on and we'll go over them together. All right, so give me a pause and go do some work and see if this is making sense to you. Okay, so let's compare and see how you did. So what I did next was I went ahead and took row 1 and column 3. So in the result, it will go in row 1, column 3. I take each number moving left to right and top to bottom. I take the first number in the row times the first number in the column, and then I take the second number in the row times the second number in the column, third number in the row times the third number in the column. And there has to be the same number. That's why those inner dimensions have to match. And I ended up with an 8, right? Now for the next one, I was missing row 2, column 1. So I took row 2, column 1, again, multiplying the first element in the row by the first element in the column, and so forth until I ended up with a 2. And then the last one was row 2, column 2. So I multiplied each of those elements together. And when I was done, I got negative 4. So I ended up with this matrix, which is the product of the original 2 matrices. This one was a 2 by 3. This was a 3 by 3, but their product is a 2 by 3. Let's now turn our attention to problem number 13. And let's first decide whether or not we can even do the multiplication. So the one on the left is a 2 by 2, and the one on the right has 2 rows and 1 column. So it's a column matrix, but the inner pair does match. I have 2s for the inner pair, and that means my result is going to be a 2 by 1, which means 2 rows, 1 column, which you see here. So go ahead and pause the video, then turn the video back on after you've completed this matrix multiplication. You can tell here that because there's only 1 column, you'll have to be multiplying by that column both times, but we have 2 rows on the matrix on the left. So to go in the 1, 1 position, row 1, column 1, we use row 1 and column 1, the only column we have. And when we multiply across, we get 30. Then to go into the second row, first column position, 2, 1, I take the second row and first column. So that gives me 2, 1. And when I multiply those together, I get 36. So my final matrix, this 2 by 1 matrix, is 30, 36. Right? Now let's go ahead and take a look at another problem, which is 2 2 by 2 matrices. So they're both square. And we want to look at what A times B is and what B times A is. So I want you to pause the video. I want you to go work these out, and then we'll come back and talk about our results. So let's compare and see what we did. Did you notice when you're doing it on your own that without the highlighting, it's much more difficult to do? So don't hesitate to take a sheet of paper and put it underneath like a sticky note and put it under the row you're working with, and another sticky note next to the column you're working with, and then move them as you move around the matrix. This is a good way to help the brain focus on the parts it's using and ignore the parts it's not using. It is difficult without the highlighting. So when we do this one, I'm going to multiply row 1 by column 1 to go in the 1, 1 position, row 1 by column 2 in this position. Notice that in row 1, I have 2, 4, for the first coefficients. Now in the second row, I'm going to have the second row, negative 5, 3. And for column 1, I multiply by 2, negative 5. And then for the column 2 position, I still use negative 5, 3 from the second row, but now I use column 2, which is 1, 1. You'll notice that the ones coming from the second one are the same in column 2. They're both coming from column 2. And the ones coming from column 1 are coming from column 1. So there is a pattern, and you can learn to check by looking at that. And we ended up with this matrix right here. Now, because A and B had the same dimensions and they were square, the product is defined both directions. But notice it is not the same. A times B is not B times A. When we do the multiplication again, you get something different. This is common in matrices. It is rare to have A times B equal B times A. That is not common. So I hope that this is making sense to you and that you're starting to understand how the process of multiplication works. What we want to do now is take a look at 2 more problems. We have problem 15 and 16. Problem 15 takes a 3 by 3 and multiplies it in both directions. And then in problem 16, we're going to multiply matrices and then add another matrix onto it. So a little bit more complicated. Now a 3 by 3 times a 3 by 3 can get pretty long. And this is where you may want to start doing some of the multiplication in your head, with the caveat that on an exam, if it's not written down, sometimes, quite honestly, we can't figure out what you did, right? So it's always a good idea on an exam to write it down. So let me show you one way of doing that. Now, I don't have a sticky note, so I can't do that. But what I can do is highlight. So I'm going to highlight, but what I would like you to do at home is to take a sticky note and use that. So we're going to do A times B. So I'm going to take row 1 and column 1. So what would you do? You would put your sticky note over rows 2 and 3 and over columns 2 and 3 so that all you saw was row 1, column 1. Now we're going to multiply them together, but we're going to do it in such a way that I can actually I can multiply the numbers together. So when I'm looking at these, go ahead and save again. I'm going to take negative 1 times negative 2, which is 2, and hold that in my head. And then 1 times 2 is another 2, so that's 2 plus 2. Or what you can do is write down the product. So negative 1 times 2 was a 2. So I could write this down up here as 2. And then I can take the 1 times 2, and that's another 2. And then negative 3 times negative 4 is 12. So I'm not writing down everything, but I'm writing down enough. Your professor will be able to tell what happened probably when they look at this. Now that I'm done with that, I want to move on to a different row and column. And it makes sense on these to go ahead and just move one of them at a time. So I'm going to move the column. So I'm going to be moving across column 1. So then I take negative 1 times 0, which is just, well, 0. And 1 times 0, which is still 0. And negative 3 times 4 is negative 12. So I know I'm going to get a negative 12 there. And I forgot to write the other one down. So I should probably come back and write that one in. That would be 16, right? And then I can do this as I move across. Now, unfortunately, it's very hard to erase when you highlight. So you'd have to rewrite and rewrite. And that's why I recommend the sticky notes. It makes it a lot easier to do. So you would need at least 2 sticky notes on each one. 4 would actually be better so that you can do the middle column and middle row. All right, let me go ahead and work through these others more quickly, and then we'll move on to B times A. So now I'm going to do the third row. And this is going to give me negative 1 times negative 3 is 3. 1 times 3 is 3. Negative 3 times 4 is negative 12. And that will give me 6 minus 12, which is a negative 6, right? Now, if you get really good at it, or you're really good at arithmetic and holding these numbers in your head, you can add them up as you move across. But again, when you do that, it's more likely that you'll make mistakes. Now what we want to do is move on, and we want to highlight row 2 and column 1. So we want to erase this one and this one. So now we've got -8 plus 2 plus 8, which gives me 2. And then I move the column over. And I know the first 2 are going to zero out, so I really only get -2 times 4, which is -8. So that one's easy. Notice when you have 0 entries, it's a lot simpler. And then I'll highlight this one. And this would give me -12, 3, and -8, which would give me -20 plus 3, -17. All right. So go ahead and pause the video, work out the last row, and then turn it back on and we'll compare. So compare your row 3 to my row 3 and make sure that you're following the same process. Hopefully I haven't made a careless mistake here. When we're looking at B times A, notice that because the order is reversed, we need to get the matrix B on the left. It's very hard to follow the process. They're not actually written in the right order. So I went ahead and wrote them over here. So go ahead and pause the video again, work out B times A, then turn it on and we'll compare our results. Recording in progress. Let's compare and see what we get. Hopefully I haven't made a careless mistake here because I did not write them down. What I did was I used my finger to go across the row and down the column, multiplying and combining the products as I went. So that's much more risky, much more likely to have careless mistakes, but hopefully I haven't messed this one up. Now, the last question on this problem is, if they're square matrices, does A times B equal B times A? And the answer is no. No, obviously not. They're not the same matrix. All right, we have one problem left to look at in this particular section, which is problem number 16. Now, in problem number 16, just like in arithmetic, you have to do the multiplication before you can do the addition. And that's because the addition can't be done until the dimensions are the same. And right now, of course, you don't have that. So we're starting here with a 3-row by 2-column matrix being multiplied together by a 2-row by 2-column matrix added to a 3-row by 2-column matrix. Is this going to work? Check the inner pair on the product. Yes, they match. So I get the outer pair, which is a 3 by 2. Can I add a 3 by 2 to a 3 by 2? Yes, I'll get a 3 by 2. Go ahead and take some time, write down these problems, and then do the problem, turn the video back on, and we'll compare. Okay, let's walk our way through this. I'm going to take row 1 times column 1, and those products are going to go here in the 1, 1 position. Then I take row 1 times column 2, and those go in row 1, column 2. Then I take row 2 times column 1, and those go in row 2, column 1. Then I take row 2 times column 2, and those go in row 2, column 2. Row 3 times column 1 goes in row 3, column 1. Row 3 times column 2 goes into row 3, column 2. I can't do the addition until I've completed the multiplication. When I took the product, I got this 3 by 2 matrix added to this 3 by 2 matrix. Then I add the corresponding positions. So 16 plus 1 gave me 17. -6 plus 2 gave me -4. 2 plus 3 gave me the 5. -6 plus 4 gave me -2. -9 plus 5 gave me -4. And -1 plus 6 gave me 5. I hope that you have enjoyed learning about matrices. They really are quite fun to work with. In the next video, we're actually going to look at how we can use these matrices, these beautiful mathematical objects, to solve very complicated, large linear systems of equations. And I hope that you will join me for that video.